Today on the Space Times podcast, we have a very special guest, Trevor Smith, CEO of Atomic-6, here to talk about his business, the products of space armor Lightwing, and some new customers like Portal Space Systems, and diving deep into orbital data centers, particularly surrounding his partnership with Sidus Space and Lonestar Data Holdings. Trevor Smith, it's a pleasure having you on the podcast.
Yeah, thanks, Harrison. Thanks, Paul.
Yeah, it's great to have you on, Trevor. I wanted to just sort of briefly start us here on Lightwing. One of the big hurdles that we see in solar power scaling solar power on orbit has been effectively cost per kilowatt or cost per kilowatt hour of power or energy, respectively. On a fundamental level, your tech stack allows for some substantial weight savings and mass savings and provides improved performance on orbit. Can you help us just sort of quantify and better understand the cost impact of Lightwing?
And also on insurance and risk mitigating, I would add that to the mix. Operational costs are not just launch costs and buying the product, but also operating. So, when you look at Lightwing, I think one of the many reasons why it's high performance, reliable, it's built for reliability. We wanted to eliminate as many failure points as possible. So when you look at a pantograph system or a scissor lift, as I like to call it, or those typical sort of hinge deployment mechanisms, you've got hundreds, if not thousands, of failure points, right? So each little bolt, each little nut can all be a failure point. They can cold weld. You had, I think it was about a year and a half ago, Viasat had a $410 million insurance claim because of a failed solar array deployment. Something that the insurance industry is very aware of, right? So if you can get rid of most of the failure points, you can increase your reliability out of the gate. And because we are replacing those metallic systems with a composite system, it becomes more lightweight, right? So we looked at how do you deploy large surface area in a very stable, very lightweight, productized way. So we looked at what was on the International Space Station. Redwire built the ROSA, Rollout Solar Array, and those solar cells are rollable. And for that type of solar array, you need a specific solar cell. We wanted to build a product that was agnostic to the mission set, which means we can put any type of solar cell on our system. So we have a deployable system. It's kind of like a rollout solar array, but instead of a slit tube like you see on the ROSA, because the tube doesn't quite have a closed cross section, our tube has a closed cross section. So you deploy that out, you get higher stiffness with that. There's some pros and cons to closed cross section versus open, but in general, you get more pros with the closed cross section from a performance perspective. So you have a stiffer system, and instead of a roll out, the back sheets are not roll out. We designed a Z fold or M fold. M fold being you can kind of fold flat in parallel with the deployer. Z fold, you sort of fold up perpendicular to it. It allows us to do terrestrial cells, silicon cells, multi-junction cells, because customers across the board, they all have different mission sets, and so you need to be able to address those different mission sets.
Yeah, and one of the key features of Lightwing is that it's redeployable, and as you mentioned, the fact that it's a stiffer design seems like it's very targeted towards RPO. Also, like berthing docking operations, where being able to close up the cross section of the satellite becomes important. Is that kind of the driving factor that led you towards that design? If not,
so the retractability was kind of a byproduct of being a risk mitigating structure. So when we built the hinges, our hinges look a little different than what you would normally see. So I'll show you on the video here, but our hinges are a composite memory shaped hinge. So there's no metal in it. And we cure it in the closed position, meaning if the array is closed, this is the position that we cure that structure in. As it deploys out, that hinge bends outward, pulling tension on the back sheets and allowing that system to deploy. What that also does is if you wanted to retract it, you turn the motor and it just wants to go back in that original cured position. So if you have any issues upon deployment, guess what? Retract it and then redeploy. But to your, Harrison, to your point on the RPO missions, there are lots of advantages and ConOps that open up, concept of operations that open up when you have the ability to retract. So in the case of Portal, as an example, right? You just mentioned Portal because they're going to fly space armor. they have a high delta V capability, so they can move really quickly. If you wanted to press the gas pedal and get somewhere really fast, today's solar arrays would rip off because of the inertia at full deployment. So the idea is retract your arrays, press the gas pedal, and then redeploy once you get to where you're going. Just one example. Yeah, so a few other examples. If you wanted to have a higher resolution picture, you can retract your arrays, lower the center of gravity and the jitteriness of the spacecraft, increase the higher resolution. If you're worried about debris impact, like the International Space Station is constantly having to maneuver around high debris areas, you could bring your arrays in, buckle down the hatch, if you will, minimize those debris impacts, and then redeploy. If you wanted to change the visual signature of your spacecraft, maybe no longer looking like a satellite or a normal satellite, you could bring your arrays in, confusing other camera systems looking at you, may not look like a normal satellite. If you want to land on anything, like an asteroid landing or lunar landing, you could bring your arrays in, land, and then redeploy, making that mission much safer, mitigating those risks. So just a few examples.
Yeah, that's a really interesting point you bring up because you mentioned that the joints are sort of a memory design to them. And you bring up the point that for high stability missions, it's very valuable to have a compact dynamic so that you have less jitter. This is especially prevalent in the PWSA Tranche 3 and several other of the tranches that are doing missile defense work. And one of the big problems with big floppy solar arrays is at their joints. So can you kind of go into the design of the Lightwing and how you've designed it and kind of how the joint design came about? Is there any work you're doing to stiffen that? Is there any interest you have in kind of building that out further for that particular use case?
So the array is extremely stiff, stiff enough that you could safely run optical comms on. So you can do laser communications with this, which is really important for, I think, future connectivity, high bandwidth, that sort of thing. Going back to your PWSA comment, at the base, we actually connect to the SATA, the solar array drive assembly. So we can match up with any SATA. We are agnostic to that. From the SATA, going out away from the spacecraft is our entire structure. So you have the deployer, which consists of a motor and typically two drums, one at the top, one at the bottom. That deploys the masts out. And then in the middle, you have those back sheets, right? So whether it's a Z-fold or an M-fold configuration, you change the hinges to accommodate for that payload packaging. And then as it deploys out, the back sheets are really only connected at the tie rod at the end of the array. So they're sort of floating in between the back sheets while it's in operation and fully deployed. But because the hinge runs the full length of the back sheet, you don't get movement. Well, you have to see the video, but in the up and down or side to side direction with our systems, because those hinges completely connect from the top and bottom, side to side, all those back sheets. So it's a really, really stiff array. We had this on display last year at the Space Symposium, and we had customers come up and literally smack the end of it. We wanted to see how quickly the system would settle, right? So if you've got a 1 kilowatt array, it's about 15 feet long, 3 feet wide, they would hit the end of array and see how quickly it would settle. It would settle within like 10 seconds.
Do you have any control over that? I guess, could you clarify the mechanism to expand it and contract it? You said it was a motor.
There's an electric motor in the middle that will drive think about it like a tape measure, right? So you can have two tape measures. There's a single motor and two tape measures, and those drums are being driven out and back in.
And that's separate from the SATA.
Right.
It's halfway.
Yeah, that's the SATA is where we connect up to the spacecraft.
So do you have any sort of dynamic control with that motor? Could you settle out a vibration in the array?
I'm not sure how to answer that question. You may need my COO on the call to answer that question. I'm not a flight dynamics guy.
One of my other questions though is about you said there's some memory capability to the hinge. Does that maintain the same memory over time, or have you seen some degradation over lifetime of a satellite?
So all composites, and this is across the industry, as you get those radiation hits, as the thermal cycling goes up and down, those thousands of thermal cycles, you will see a degradation in the shape of it. So how you combat with that is you add additional sort of shape, if you will, a little harder curve to combat some of that. Forget the engineering term, but the bending over time, right? Like a sagging, if you will.
Yeah.
But that's an industry-wide problem. I was also going to mention, Harrison, if you're having trouble like tumbling with your spacecraft, or you're kind of lost control, one benefit of having a retractable array is because you can bring your center of gravity in, and then it helps you gain recontrol of that system, because you're bringing those arrays in, and you can hopefully bring that satellite back under control.
Yeah, that's really valuable. I mean, we were talking about Starfish Space recently. It's another RPO company, and they had that problem previously, and I think that would help. It's the traditional dynamics situation that they teach in school. Like
I use the metaphor. Imagine a sailboat coming into dock, and it's really windy. You do not want to dock your sailboat with your sails up, right? It's way harder to do that. So if you bring your sails down, drive straight in, like an RPO mission, it's much easier to do that docking, rendezvous proximity operations and docking mission without those large solar arrays sticking out the side.
Yeah. And I asked about the dynamics of the solar arrays because there's a company called Samara Aerospace that's doing a similar approach to that, of using dynamic actuation at the joints of solar panels to
I've seen that. I actually have seen that. I think we maybe could like implement that into our system.
That's kind of where my question was coming from.
Yeah.
Following on with the increased sort of dynamics and control capability that you're able to get just by the nature of modifying one's moment of inertia while on orbit, there's extensive there's extensive value add that Lightwing brings to your direct customers. Tell us a little bit about who your sort of beachhead customers are, who the current users and adopters of Lightwing are, and sort of where you see the technology going. Like, what are you most excited to see Lightwing used for in the next like 5 to 10 years that either isn't fiscally or physically possible today?
Sure. So, I think we can all agree that compute will continue to grow, right? So you need more power. Everything's going to be more power hungry. You're going to need more compute capability, which means you need to generate more power. And potentially you need radiative capabilities if you're in space to get rid of all that heat. So Lightwing, if you look at large solar arrays, like what's on the International Space Station, I think it's about 15 or 20 kilowatts or 20,000 watts. Physics necessarily tends you to move towards a deployable composite solution, just because a pantograph, at that scale has so many failure points and it becomes so floppy. You need a very, very stiff, lightweight system. So I think systems like Redwire and like Lightwing, what we've built, are really, really great for that. So I'm excited to see more power-hungry applications in the space arena. And ironically, the very first space contract we signed, we announced it early last year, was with Sidus Space and Lonestar Data. So Sidus is building the spacecraft, Lonestar Data is the customer, and they'll be doing orbital data centers, storage in the cislunar environment. So we're going to be building the power system for an orbital data center in lunar orbit. And I believe that's the first one I've ever heard of. So I'm excited to see larger, more power hungry systems get up there, because the more power hungry the system is, the better application and use case that Lightwing can bring. And because we've built this from a productized and modular fashion array, we can kind of cut to length. Like a 1 kilowatt and a 3 kilowatt array look the same except for the length. So the diameter of the mast is the same, the hinges are the same, the deployer, the backsheets, all of it's the same, which lowers the cost on a per kilowatt basis, right? So we can become very, very competitive, especially in the large array systems or large deployable surface area systems, because of that unique productized nature of how we built it.
It sounds like you view the primary sort of failure point for scaling solar power on orbit. It sounds like you view the primary failure point as one of a mechanical or dynamic, effectively as a stiffness problem, not as a mass problem, not as a power generation problem, not as a cooling problem. Am I sort of hearing and understanding that correctly?
Mass is always going to be a problem, right?
Mass is always a problem. It's
always a problem. And if you're bringing in orbital data center from a compute perspective, thermal is the other problem you have to have. And you need surface area for both of those, right? So the beautiful thing about Lightwing is it's really an architecture to deploy flat things. Does it have to be solar power? right? So we're actually looking at deploying radiators for customers wanting to do large amounts of compute. And you can deploy phased arrays. Those are also flat. Literally anything flat, this system is really well designed to deploy large surface area for. So when it comes to compute in space, you need the power. That's what the solar is deployable. You need thermal. That's a deployable radiator. And if you use phased arrays, you could do that as well. But I think they'll be using optical comms for the most part.
That certainly makes a lot of sense, and helps me better understand sort of where you see Lightwing fitting into the ecosystem. So it sounds like on orbit compute, it sounds like some of the, for lack of a better term, some of the more infrastructure type projects on orbit are some of the things that you're excited to see Lightwing leveraged for. Both on a power, on a cooling, on a structural level. You're see the options.
Space-based solar, like even if it's space-based solar power, they're not doing that much compute, but they're trying to gather a lot of power to beam it somewhere, right? That is another application. We may have an announcement about that coming soon.
Oh, it's exciting. I mean, these are like huge up and coming markets. And the cool thing is that they're very new markets for space. That's kind of a blue ocean opportunity. I could definitely see space solar power being valuable. Like when you don't want to collect power, closing it up so you're not generating extra heat is super valuable. So, I mean, across all these different applications, where do you see the most growth for this particular product? And what are you most excited about?
So I think very, very near term, it is telecommunication satellites. So mega constellations that are, call it per satellite, 20, 25 kW total, right? Spread across two wings. And ultimately, when you look at solar arrays, people go, oh, it's dollars per watt, or it's kilograms per watt, or sorry, watts per kilo. It's actually dollars per watt per kilo, because that's really what matters to the mission. You can't separate, oh, here's one metric and here's another metric. You need to put dollars per watt per kilo in. And when it comes to those three combined metrics, we are the best hands down on the planet for that. So then you throw in the insurance piece of it, which is a lot risk mitigating, and your solar arrays are going to work versus having these losses. So there are lots of opportunities in telecom. I've been, publicly stated previously, we've been about $3 billion in RFPs last year just for telecommunication type satellite systems. And then to answer your other question, longer term, I do think some compute will move to space. I think your first low-hanging fruits will be those edge cases where doing the compute in orbit is actually really advantageous instead of doing it on the ground. So you have space-based systems like maybe lots of Earth observation images. You need to do a very, very big calculation. Well, you don't want to do a downlink all that data, uplink it, right? You just move it to whatever cloud you have in orbit, do that calculation, and then beam down the really valuable data. So I think there are plenty of applications in orbit, both commercial and defense, that need racks and racks of GPU compute to do compute at the edge for those specific use cases. Will you be using Chat GPT for a pizza recipe and then compute it in orbit? Probably not for a while.
If I could, yeah.
Yeah, well, I do think there are some low-hanging fruit because, space right now is going to be more expensive than terrestrial. But that's why you need to go after the applications that really make sense and that need it in orbit from a latency perspective and lots of other reasons.
And do you have a first flight plan for Lightwing?
We do. So that'll be with Lonestar data and Sidus space.
Okay.
That will be in 2027. Starting, I think it's going to be Q2 or Q3. Right now, we are under a tactical funding increase with Lightwing to get it through flight qualification.
Great. And I know Lightwing is one of your main products. Space Armor, which I want to talk about in a minute here, is another. But your business is one that does composite services across multiple industries, not just space. So you work on marine, earth, terrestrial-based, air-based. Mention any that I left out. But kind of how do you break down your business in terms of the service to those industries? Why are the two main products you have in space? Kind of what is the level of focus you have between service and product and between the different industries that you're servicing?
So I think you have to keep the main thing the main thing. And our main thing is we can build the highest performing composites on the planet, meaning we can push those raw materials towards their theoretical limit better than anybody else. So what customers actually need that extra performance, who has the budget for that, who's willing to pay for that, that's going to be the most extreme and demanding environments, right? So space and hypersonics are kind of our two leading ones, with space being the majority of that because of that extreme demanding use case that is willing to and has the budget for high performance capability.
Yeah.
Does that help answer your question?
Yeah.
So in addition to that, we work with Hermeus. We're doing some work on their hypersonic radome. I think they've got a new vehicle going out to fly pretty soon. We've built some Group 3 structures for Delta Black and numerous other ones that I won't mention here. We've been done some ballistic projectile armor, like chest protector armor, not space armor, but actual like terrestrial.
It's what we get out there.
FYI, don't use space armor as terrestrial bullet armor because the bullets go right through. I know firsthand. I shot it with my 9mm.
Good to know.
Do you know why they go right through?
Larger size?
They're going too slow.
Oh, interesting. So does the substrate in the composite not behave like I don't know, is it like non-Newtonian in a way?
Yeah, you're getting the right direction. So I give the example, like if you slap the water with your hand versus slowly inserting your hand, right? A subsonic round will go farther into the water than a supersonic round, even though it's moving slower. Right. So our shield starts to work at much, much higher speeds than what you see terrestrial bullets move at. What's interesting, and we're still trying to test this out, we were thinking, what other applications terrestrially could this space armor help protect from? What moves that fast? If you look at small explosives, like a hand grenade, a C4, that type of thing. So C4 projectiles come out around 8 kilometers per second. We test space armor at like 7.5 kilometers per second. So we have not tested it yet as of this recording, but we do think there's a decent chance we can help protect from small explosives here terrestrially.
I really want to dig into this, but I did have one more question before we focus back on space armor, because the Hermeus one's interesting because we've been seeing a very consistent pattern across the aerospace industry in the growth of hypersonics as a market. And I know, like you said, you worked on the composites for the structures. I even saw that you worked on some project for like composites for rocket nozzles and stuff. Is there a way that you're approaching the hypersonics market? Like, where do you see the niche that you kind of fit in? Where do you think you can add value? Like, do you see this as a big potential market for you?
As funny as it sounds, so we were doing like a strategy session, trying to find out what is the total addressable market for a lot of different things, and who's willing to pay for the things that we want to make. The TAM for carbon fiber golf clubs is far greater than composites and hypersonics. Like, believe it or not, there's more money to be made in carbon fiber golf clubs than there are in hypersonic systems. That being said, we need, as a country, to be able to have these deterrent systems, have these capabilities. So it is very important. So I don't want to downplay that. The work that Hermeus is doing is really, really important. So the core value that our company brings is the unique tool set, tool being a mold that we use for these composite structures. And then we optimize that resin cure profile, right? So when you get a pizza, on the back of the pizza box, it says, cook at 400 degrees for 20 minutes, right? So the same thing as in composites, you get a resin in from a manufacturer, they go, here's how long to cook it, blah, blah, blah. It's usually wrong, or not, wrong's the wrong word, not optimized for the application we want to use it in. So we will dial in that recipe, put it into this unique mold that we have, and then cure it in an autoclave that is has some unique attributes to that autoclave. We operate at higher pressures than a normal autoclave would. So you do those three things, that enables us to manipulate those systems and push them towards those theoretical limits that I was talking about.
Very cool. And are you optimizing on a case-by-case basis, or do you have like an overall like core recipe that you keep going back to?
Each resin system is different. Each resin system is very different, right? So if you're curing for an oxide ceramic versus a carbon fiber going into space and that resin system. Those are very, very different recipes. So you have to play with the neat resin system itself, optimize that cure, and then put it into the structure.
And so going over to the space armor, I know you have a very cool announcement about it with Portal Space Systems. That will be your first flight for space armor, I believe. We saw some funding for this in development, but I believe this will be your first time testing it in space. So I was hoping you could kind of give us the rundown on this particular product.
Yeah, you're the first ones that I'm talking to about this because the embargo lifts tomorrow, so it feels a little weird. But yeah, happy to talk about it. So Portal Space, they have a really unique capability. I'm good friends with the CEO, Jeff Thornburg. For background, Jeff was one of the chief architects and really responsible for that Raptor engine that powers the Falcon 9 and Starship. So the guy knows a little bit about space. But Jeff and I became friends over the past few years through a accelerator called Creative Destruction Lab. They have a space accelerator. Actually, Commander Chris Hadfield started it. I know we were talking about
cool.
it. So I met Hadfield there and I met Jeff there. But yeah, so Jeff, their system, I can't speak to where they will be flying and all of that, but they anticipate a likelihood of some sort of impact, debris impact. And so they are placing space armor over critical systems, right? So fuel tanks, avionics, things that they can't have go down. Recently, I don't know if you saw in the news, but the Chinese astronauts got stranded because so their return vehicle, I looked it up. The news said it was something less than 1 millimeter of an impact, a debris strike.
Yeah.
So just for reference point, over 90% of debris in LEO is 3 millimeters or less. And that is also untrackable. So you don't know to move. You don't know it's coming. That's why space armor is picking up. And also, I think a week ago, the Spanish satellite, I think it was a debris strike, and it was like a $400 million insurance claim because of a debris strike.
Yeah.
So unfortunately for the space industry, I think this is just going to become more and more of a thing because we're launching more things into space. Kessler syndrome, if you're familiar with that. I spoke with Don Kessler a few months ago, really nice guy. But I think you're going to start seeing satellite operators, builders, bus builders start implementing protection from the early days into their system designs, because this is just going to become more and more of a thing. The benefit of this, though, as you mentioned, Harrison, as opposed to a Whipple shield, because I know you talked about this on a previous episode, the Whipple shield, when you hit it, there's secondary debris impact, post-impact ejecta. So what you see a video on our website, there's a metallic shield and then there's space armor. The metallic shield gets hit and more debris comes out, is delaminated from that monolithic block of aluminum than the original mass of the projectile coming in. The unique thing about space armor is that there's really no harmful secondary debris creation. So that video is at 1 million frames a second. I've watched it 100 times. There's the idea that we could not just protect our spacecraft, but also help minimize additional debris creation, I think is a great thing. And a total byproduct of us building this. A total accident.
Yeah, cleaning up space.
Yeah.
One of the things that I want to follow up on with regards to space armor is the growing market, I'll say, of secondary or aftermarket space assets. We've seen a multitude of different companies that are focused on refurbishing and deorbiting existing assets on space. They go up, they come back down, they get refurbished, and then they get back up again. So there's obviously some unique and special needs. There's a lot of efforts going towards specific types of heat shielding so that assets can be brought back down through orbit. There's multiple different vehicles that are looking at potentially grabbing assets and then returning them safely themselves. And those will need specific types of touching and inflammation. And I'm curious, how do you see that sort of, I'll say, that used car market for satellites developing, and where do you see space armor sort of fitting into that, in so many words, of protecting the assets that are up there while they're up there?
So space armor is designed for demisability. It is not a heat tile, right? You don't want to use this for reentry. So it will demise upon reentry, which is what you want from your deorbiting satellites, because you want them to demise and not come crashing into Earth. So while reusable satellites, there's lots of people working on it, I think are great. the satellites that are up there, our goal is to keep them operational longer, reduce the risk of impact and mission loss, and hopefully last longer than their anticipated mission.
So you don't necessarily see away, or you don't necessarily, it sounds like, view space armor as a method of helping to tackle that sort of used car market. Not certainly not as a method of reentry itself, but as a core component of, you need to rust proof your car, you need to rust proof your satellite before it goes back up. So like space armor fitting into that ecosystem.
Sure. Yeah. So that's exactly why we wanted customers to be able to implement this into the vehicle very easily. So we have 6-inch hexagon shaped tiles. And so Portal, as an example, ordered multiple tiles and they will put them next to each other and really cover the surface area that they want using that hexagon shape. Does that make sense? It makes it easy to like puzzle piece the areas that they want to protect. So if you've got a satellite going back up into service, a used car, and you're like, hey, I'm worried about this area, maybe it already got impacted or we added some critical component, you could very easily slap a space armor tile on the outside and protect that area on your used car, so to speak. What's also unique, we haven't talked about it yet, but to my knowledge, space armor is the very first radome ever built for space. So the uniqueness of the material set not just stops space debris, it allows for radio frequency transmission through it. And then we have a version that also can block it. So for certain customers, parts of the spacecraft, they want RF transmission through it. And other parts of the spacecraft, they actually want to block that transmission, whether it's for interference or numerous other reasons. But we can basically have an RF permeable and RF blocking version of space armor, which opens up lots of new ConOps because no one has ever been able to protect their communication system from a debris strike until now.
Yeah, that's super valuable, especially when we talk about like AST Space Mobile and their giant like deployable phased arrays. I know you brought up phased arrays as an option there. So like as these comms payloads get bigger like that, they're going to be a bigger target.
Yes, that is for sure.
So I know you mentioned that the space armor was rated to 7 kilometers per second, and I believe space armor max is up to 1.2 millimeter size debris.
So you just mix some metrics there. Space Armor Light is rated for 3 millimeters and less. Space Armor Max is 12.5 millimeters. What has gone through flight qualification and what Portal is flying is the light version. We have not finished qualification on Max just because we had customers out of the gate asking for that 3 millimeter protection because they're unmanned systems and just don't need that higher level of protection.
And when you fly on Portal, is there something you're testing for? Like, is there a way for you to tell if the armor gets hit? Or is
fortunately or unfortunately, I hope Portal gets hit, but just gets hit in the right spot. So they are going to be flying with the tiles on there, and they'll have cameras. I think they'll have at least 1, maybe 2 cameras pointed at space armor. So you won't see the moment of impact because the projectile will be moving too fast. But you will see the before and after, and you can compare the telemetry on the spacecraft to see if anything bad happened, right? So in an ideal world, the camera will show a before with no impact, and then there's a bullet hole, if you will, in that front part of the shield, and then you confirm with telemetry that nothing bad happened to the spacecraft. That is the best case scenario for us over that 5-year period. I hope it happens on day 1.
So is that how you expect to measure it in production when it's deployed to a larger set of satellites? Or
so I mean, I don't know that everyone will want to monitor them all. I think long term, we have been talking about embedding sensors into the armor itself that you can tie back into the spacecraft if you're really worried about it, which, Paul plays into the insurance side of the things because you could relay live data on debris strikes on your constellation if you have embedded sensors into the space armor tiles. So you know where you got hit, how bad you got hit, how often you're getting hit. And that data could inform the underwriting for these space insurance premium folks.
Yeah, and I think we saw this recently with a company called Odin Space. They're building a radar sensor for satellites as sort of a black box to track collisions with the spacecraft in order for what you said to underwrite insurance claims. So I'm really interested in kind of the interplay here of defending against and actually like proving you've defended against something.
Yeah, there were a couple of people we've talked to at Space Force, and we're like, would you be willing to fly directly into a debris field? Actually, that sounds kind of fun.
Yeah, some Han Solo stuff there.
Yeah, but most customers will not want to do that. But they do want that protection because of the things that they can't track or see and know to move. So that's why Space Armor is there.
And so going back to the ratings that you gave for the Light and the Max, they both seem pretty tailored towards the low Earth orbit environment, where there is a lot of small pieces of debris that have built up over the years, paint flecks and whatnot. And 7 kilometers per second is coincidentally kind of the orbital speed at that altitude.
Yeah, it's 7.5, depending on where you are. And if you, for some reason, get hit in retrograde, you're looking at 14.
Yeah.
Which there's no hypervelocity gas gun on Earth that can hit that speed. We're maxing out the gas guns at Texas A&M at like 7.2, 7.5. Don't quote me because it kind of changes with the size of the diameter and the mass. But yeah, we're trying to just test for the most broad use case in LEO because that's where all the debris is. And as you go out to MEO and GEO, those velocities will go a little slower.
Okay. So do you think it's still something that can be used in GEO? Because as you mentioned with Hispasat last week, it got hit at like 50,000 kilometers out. And China just submitted for approval proposal for 200,000 GEO satellites being put into orbit, as well as all these interactive RPO demos going on in GEO. So I think there's a lot more activity that's going on out there. Is that a market that you see as complementary, something you can expand into?
Well, so as you move out in orbit, the projectile orbital velocity gets slower, right? So the closer you get to Earth, the faster it is. You got to GEO, it gets a little slower. So it's an absolute market. We were optimizing for the most customers and the highest speed, which would be the highest bottleneck for protection. But as you go out, absolutely. And again, I don't know where Portal's going to be flying, so maybe they're taking it. I don't know. We'll find out if they, let us talk about where they fly.
And is the space armor something that you would be able to like layer up if you kind of built a Whipple shield out of it? Does it increase its capability or is it diminishing returns?
I mean, you're adding additional protection. Sure. We've had some customers ask, well, if we get hit and we had a robotic arm, could we apply another tile in space with this robotic arm and just put it over the one that got hit? Absolutely. That's why it's made in a tile form. So like you could think Pez dispenser, you've got a robotic arm and place it. Like today, that's what they do on the ISS, but instead of a robotic arm, it's astronauts. Not a safe thing to do, right?
Yeah. And it's interesting thought as we get more towards reusable and orbital refueling depots, and a lot of these kind of portal-like companies can do more than one mission.
I would love to see space armor inside an astronaut suit doing spacewalks.
So you had a really interesting kind of entry into the space industry. I know you founded a company before, but I also noticed that you've had like a Beer Street Journal and you have your own podcast, driving around hypercars. So, what is space the coolest thing to you, or is it driving supercars, or, what do you think of the industry that you've been working for years in now?
Space is the coolest thing. Beer was fun, but actually, I think you're the first person to bring that job up. No, the Full Burn podcast that I do is a way for me to interact with really unique, awesome people in the space industry and have a good time doing it. And so I just enjoy doing that podcast. There's no sponsors. I don't really look at the views. I just do it to connect with those founders that we're interviewing on the podcast. And we happen to be doing it in Ferraris and Lamborghinis and speeding on occasion.
Awesome. Yeah, Trevor, thank you so much for joining us. It's been a fascinating conversation, learning about your background, learning about everything that you're working on at Atomic-6, and sort of where you think the industry is going and what you're building and designing for. How can we and our listeners help you? What are you looking for? What do you need these days? Tell us about it.
I need smart engineers. I need smart people. I need people who want to be on the mission with us. Right. We need to grow the team. So there's that. We want customers who need lots of power and protection with Lightwing and space armor. So would love to talk to bus builders or end users for that. And just a general excitement about the space industry, I would say, right? Just be excited about the industry, because I think we are like Space Race 1.0 and we went to the moon. It's the Wild West right now. Like Musk might make his own laws on Mars if he's the first one there, and like these weird, like it's basically international waters. I think it's such a unique time to be in the space industry because the rules haven't really been set. So I can't wait to see what gets set and who sets it.
Awesome. Well, anybody interested in joining Trevor's team and contributing to Atomic-6, the Lightwing, the space armor, by all means, we'll be sure to put in touch. And the same goes for anybody looking for their capabilities on their assets themselves. For all of us here at the Space Time Podcast, I'm Paul Mayer with Harrison Lambert. We're glad that you all joined us, and we look forward to chatting again soon.
Yeah, thanks so much for joining us, Trevor. I look forward to following your success with Atomic-6 and keeping track on your Full Burn podcast.
Thank you. Thank you, guys.